is lesson 4.0, Prerequisite Skills for chapter 4, which is all about trigonometry. So we're going to define trigonometry. What shape are we talking about when we're working with trigonometry? Circles? Squares? Triangles? Pentagons? Triangles. So trigonometry is the study of relationships found in triangles. So relationships, well, the relationships between sides, the relationships between angles, the relationships between sides and angles, all those sorts of things are going to come into play. Some things we need to know about Pythagorean Theorem. What is Pythagorean Theorem? When can you use it? When are you allowed to use it?
I don't know, but it's like a squared plus b squared equals c squared.
Yep. Only used in right triangles. And you are right, it is a squared plus b squared equals c squared. But you can also use it in other forms, right? Like you could subtract b squared from both sides, then you'd get a squared equals c squared minus b squared, right? That's just using algebra to rearrange it to solve for a different side. So what's going to end up happening in trigonometry is that we're going to end up creating a lot of right angle triangles. And then we can use the Pythagorean theorem and other related theorems in order to help solve certain things in the triangle or to find the relationships of sides and angles within a triangle. Okay, you have a triangle there. What we want to do is talk about opposite, adjacent, and hypotenuse. So I'm going to quick sketch this triangle. It's got a right angle right there. You should note that because Pythagorean theorem is only used in right angle triangles. And we're going to label our sides. And typically when we label our sides, the longest side is always the hypotenuse. And because we're using a squared plus b squared equals c squared, the hypotenuse is going to be c. And then for our other sides, it doesn't really matter what you name them, a or b. What we want to do is talk about opposite, adjacent, and hypotenuse from angle A. So I'm going to do that in blue. Which side is opposite angle A? Is it side A or side B or side C? Which side is opposite this angle? Side A is up. Okay, so in blue I've got up. Which one is adjacent? Side B. And side C is going to be the hypotenuse. Okay, I'm going to take a new color and we're going to talk about angle B in a new color. And the hypotenuse is the same. It's always going to be the same. This time, B is opposite and A is adjacent. Okay, so they do change their name based on whichever angle you're talking about. So if you're talking about angle A, you need to notice that side A is opposite angle A, but side B is opposite angle B. So that will change how we use our primary trig ratios as well. The trigonometric ratios are also only used with right triangles, only used in right triangles. And they are represented by SOHCAHTOA, or I like to write them SOHCAHTOA. And hopefully you have room there to record each one, what they actually mean. So the sine of an angle is equal to the ratio between the opposite side and the hypotenuse. So a ratio is just a comparison of numbers. So right here we have a ratio. one number over the other number, and the sine of theta, the sine of the given angle, or the angle that you're looking for, is equal to opposite over hypotenuse. So this is called the sine ratio. We also have a cosine ratio, where the cosine of a given angle is equal to the adjacent side of the triangle over the hypotenuse. And the last primary trig ratio is tangent. The tangent of angle theta is equal to the opposite side over the adjacent side. So you can use this to go both ways. You can use this to find an angle if you have two sides, or you can use this to find the side length in a right triangle if you have the angle and one side. And you just have to choose the correct ratio to use depending on the sides that you're interested in working with, and then apply those primary trig ratios, which we will do. So we're given a triangle ABC. We're not given, they didn't draw it for us, but we could draw it if it was going to help us, which it might. So we are given that AC equals 4 centimeters, BC equals 1.5 centimeters, and angle B equals 90 degrees. So if I was going to start this, I would start with my angle B, which is 90 degrees. And I don't know, do I know how long those lengths are? I know BC is 1.5 centimeters, so I'll shorten that up. And AC, which is going to end up being my hypotenuse, is 4 centimeters. So this triangle is going to look something like this. We're given BC, 1.5 centimeters, and AC is 4.0 centimeters. And our goal is to solve the triangle. What does it mean to solve the triangle? Okay, to solve means find the measurements. If you need this note, put this note somewhere, of all sides and all angles. Okay, how are we going to do that? Well, we can use Pythagorean Theorem in a right triangle to figure out our side lengths. So I already have my hypotenuse and one of the legs. So I could do it like this. In order to find the length of AB, I could say that AB squared plus 1.5 squared equals 4 squared. And then there's two ways you could do it. You could figure these things out and then do algebra, or you can kind of rearrange this using algebra and then solve. I'm going to move it around a little bit first. So I'm going to subtract 1.5 squared from both sides. So I've got AB squared equals 4 squared minus 1.5 squared. And you could even go one step further and take the square root of both sides, so that you end up with AB equals the square root of 4 squared minus 1.5 squared. And you could put that whole thing in your calculator pretty much all at once if you know how to work your calculator well. Otherwise, you can just keep on breaking it down. You've got 16 minus 2.25. So you're looking for the square root of 13.75. And you can put that in your calculator. And you would get AB equals 3.7 centimeters. So that's how we get the side length there, just using Pythagorean Theorem and rearranging it a little bit. But what about our angles? Do we have a tool that helps us get the angles in a right triangle? Yeah, the primary trig ratios, right? So, ka, toa. Okay? Well, let's look for angle C first, okay? If I'm looking for angle C, I don't want to use the side length that I figured out because it might be wrong and it's at best an approximation because I converted it into a decimal here. So I'm going to use, with regard to angle C, I have adjacent and hypotenuse. Adjacent and hypotenuse tells me that I'm going to be using cosine. Here's how you use the primary trigonometric ratios. This tells me that the cosine of C is equal to the ratio 1.5 over 4. In order to find out what the measure of angle C is, I need to undo this cos C. I need to take the inverse cosine of both sides. Okay, so angle C, the measure of angle C is, and here's how we write it, the inverse cosine, the cos with a superscript -1, of 1.5 over 4. Okay, again in your calculator there's two ways to do this. You can probably just punch this in, second function cosine, bracket, 1.5 divided by 4, close bracket, enter. If your calculator cannot do that, then you can do 1.5 divided by 4, enter, and then go second function, cosine, second function, answer, and you'll get the same thing. So the measure of angle C is, what did you get?
Wait, did you shift answer?
Depends on which way you punched it in. So you should be able to go second function cosine, open bracket, 1.5 divided by 4, close bracket. Okay, so now to find angle A, are we going to do this whole process again with different numbers? Yeah, we could do it again and we'd get the right answer, but we know two of the angles, so we just need to know that the sum of interior angles in a triangle is 180 degrees. This guy, angle B, is already 90, so I know there's actually only 90 degrees left to share between A and C. So I'm just going to write that angle A is equal to 90 minus 68. Angle A equals 22 degrees. And because I was asked to solve the whole thing, and there's a bunch of work here, I want to keep my work organized. I'm going to at least box everything that I find out. Often it's even easier at the end. Just write it down on the side. Go AB equals 3.7 centimeters. Angle A equals 22 degrees. Angle C equals 68 degrees. Box that, and then move on. Okay, another tool that you can use when you're working with triangles is the Sine Law. The Sine Law you can use in acute angle triangles. It doesn't have to be a right angle triangle. So we use, and the key to knowing when to use it is we use when we have opposite information. When we have opposite information, what does that mean? That's not any kind of technical math term. It just means you can use it when you have an angle and a side that are opposite each other. If you have a finished ratio of the side and the angle, then and one other piece, whatever that piece may be, then you can use it to find the rest of the triangle. Okay? So I'm going to write down what the sine law is. You can use it in two different ways. When you're looking for an angle, it's easiest to use it this way, where you create three ratios. And it turns out that these three ratios are all equal to each other. So if you take the sine of angle A and divide it by the length of side A, that's the exact same value as taking the sine of another angle and dividing it by the length of its opposite side. And it's the same with the last side and angle as well. So that's why you need what we call opposite information, because you need one of these ratios to be complete, and then you need one piece of one of the other ratios. So out of the four pieces, you need three, and then you can find that missing piece. Hopefully that all makes sense. You can also write the sine law this way. This is the easiest way to use it if you are looking for a missing side length. You put the side length in the numerator, and if you know the angles, then you put the sine of the angle in the denominator. And again, all of these ratios are equal. You only need to use two pieces at a time, so two ratios at a time. So you might use these two, and you need to know the opposite information and one other piece of information in order to find that missing piece. Okay? Good. Quick example. In triangle HJK, angle J measures 74 degrees. So if I was doing a sketch, I would just go ahead and start with the angle that they give you of 74 degrees. So it's not quite 90. It's bigger than 60. Something like that maybe. 74 degrees. And that's angle J. HJ is 8 centimeters and HK is 10.4 centimeters. So HJ, let's just call that H then, and we'll name this 8.3 centimeters. And then HK is 10.4. So I'm going to make this a bit longer maybe. And this diagram is not very good. You can change it as needed, but whatever you get, doesn't really matter. HK is 10.4. You don't trust your diagrams anyway, you trust the math. And we need to calculate the measure of angle K, and we're given J is 74. So I know I can use sine law here because I have opposite information, right? I have the measure of angle J and I have the length of side J. I'm looking for the measure of an angle, so I'm going to use this form, and I'm just going to rewrite it first. I've got the sine of K over the side length K is equal to the sine of capital J over the side length lowercase j. Then I can go ahead and sub in the values that I know. Okay, I don't know the sine of K. I know the side length K is 8.3. And I know the angle J, so I'm taking the sine of 74 over 10.4. So again, you could change this into a number. You could do sine of 74, enter, divided by 10.4, enter, times 8.3, enter. That would work, but you'd be rounding every time, and to record it on your paper isn't as nice. The easiest way to do this, I would say, is, well, you could multiply both sides by 8.3 first. So you'd get, on the right-hand side, a numerator of 8.3 times the sine of 74 over 10.4. Now that you could punch into your calculator, and then you would take the second function sine of that answer. So you're taking the inverse sine of both sides, which is going to tell you that the measure of angle K is going to be equal to the inverse sine of this whole thing. So I'm just going to rewrite the whole, I'm not actually going to rewrite the whole thing. I'm just going to write ANS because that's what I would do in my calculator. And that just means the value of this whole thing goes in that bracket. Okay? Hopefully you're trying this on your calculator, but if you were to punch that whole thing in, you would end up getting angle K measuring 50 degrees. Okay, the last law that we have to review that helps us in solving triangles is the cosine law. Cosine law, which looks like this. You can write this under your line. When can we use cosine law? You can use cosine law when you have when you have two sides and the contained angle What does that mean? That means you have side, angle, side. So you have two sides right beside each other and the contained angle. And then you can use it to find this opposite side. Okay? Or when you have all three sides. Side, side, side. When you have side, 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 you can use this in a different order to find any one of the angles. Okay? So two applications of the cosine law. And here it is. A squared equals b squared plus c squared minus 2 times the product of b and c, so 2bc, times the cosine of a. That's just one way to write it. Okay, that's when you're looking for the side length a and you already have b, c, and the angle a. The angle a will be right in between side length b and c. You could write this two other ways. You could write it with respect to b squared, then it would be a squared plus c squared minus 2ac cosine b. Or you can write it with respect to c, then it would be c squared equals b squared plus a squared minus 2ab times the cos of c. The key to notice when you're remembering how to use this is that the side length that you're looking for is way over here, and its opposite angle, its angle is always the one on the end. So when you're looking for side length A, angle A is at the end. When you're looking for side length B, angle B is at the end. And the other two side lengths are in the middle of it twice. Okay? The other thing to remember is that this whole piece is all multiplication. It's 2 times b times c times the cos of a. Okay, these are all just multiplication in between there. So you add up the square of b and c, and then you subtract this big chunk from it. Okay, that's how we write it when we're looking for a side length, but you can also write it to help you look for an angle, in which case it's the cosine of, that's awkward, it's the cosine of A is equal to b squared plus c squared minus a squared over 2bc. So in this situation, this is when you have side, side, side. You know all of the side lengths and you're looking for an angle. Okay? And just like you could write the top format 3 different ways, you can write this one 3 different ways. I'll just write it one more way, but if you were looking for the angle b, you would use cosine of b, and then your angles that get, or sorry, your side lengths, the squares of your side lengths that get added together are going to be a squared plus c squared minus b squared. And in the denominator you have 2ac. So again, here you're remembering that the angle that you're looking for, that's the side. The square of that side gets subtracted from the two top ones. Same thing here, right? We're looking for angle A, so the side length A squared is the one that gets subtracted from the other two, and it's not in the denominator. The other two are in the denominator. So you can see some parallels between what's included where in these. We're not going to show how they derive from each other because you did that in grade 10. We're just going to apply them. In example 3, triangle CDE. We are given angle C. Again, you don't need to draw these. I just draw them because it helps us visualize it. But we're given angle C is about 56 degrees. Let's say that's about 56. And that is angle C. CE is 4.7. Let's call that 4.7. Call that E. And CD is 8.5, so it's going to be quite a bit longer, like that. So this triangle looks something like this. CD is 8.5 centimeters. So what situation do we have? We have side, angle, side. We have two side lengths and the contained angle. So I can set this up And what are we looking for? We're looking for the length of ED. So we're looking for this other side. So I can set this up. I can say ED squared is equal to CD squared plus CE squared minus 2 times CE times CD times the cosine of C. It's a bit more awkward to write when we name our side lengths by their capital letters. It's easier if you use the lowercase letters. But anyway, here's what we know. We don't know ED squared, but we know CD is 8.5. We know CE is 4.7. Don't forget your little squared on top of each of those. Okay, we haven't done that yet. And it doesn't matter which order I plug this stuff in because it's all just getting multiplied by each other. But anyway, we got 2 times 8.5 times 4.7 times the cosine of 56. Still looks a bit confusing with the cosine of 56 in there, but that's really just a value. I could punch that into my calculator and get a value, which is what you would do now. And I would typically do this in 2 parts. I would do 8.5 squared plus 4.7 squared. That would be 1 part. And then I would do this whole chunk. What you could do is you could get this answer and then hit subtract, and then in brackets do 2 times 8.5 times 4.7 cos 56. Close bracket, enter, and you will get the right answer in your calculator. I'm not going to do that. I'm just going to give you the answer. The answer here is DE. By the way, when you do get that answer, you'll still need to square root both sides. But here we go. DE is, you should get 7.0 centimeters. Without showing all the work. And example 4, again, we're going to try to sketch this thing out. Doesn't really matter how good your sketch is. You don't trust your sketch. It's just to give you an idea. Here we're given all 3 sides. So I have a side length of 8.1, side length of 5.9, and a side length of 9.2. So I've got a longest one is going to be 9. That one's going to be my 8, and that one's going to be my 5. And then I have to name them correctly. So let's go GJ is 5.9. JH is 9.2. I don't even think I made my longest one. Put J there. G there. Now I can make JG 5.9, HJ 9.2, and GH 8.1. Okay, now I'm given 3 sides, and I want to find the measure of angle G to 1 decimal place. So the cosine of G is equal to, and I'm just going to use, I'll use my lowercase letters here. So this side is J, this side is G, and this side is H. That'll make it a bit easier. So angle G, I've got H squared plus J squared minus G squared in the numerator, and then in the denominator I have 2 times H times J. Plug in all the numbers that I know. In the numerator, 5.9 squared plus 8.1 squared minus 9.2 squared all over 2 times 5.9 times 8.1. And if you're using your brackets properly, your calculator can do this all at once, or you can easily just do it in 2 different things. You just have to be careful that you don't hit divided by 2 and then times 5.9 times 8.1. You have to make sure that this is all bracketed together as a group. Okay? And if you do that correctly, you should end up with a measure of angle G that is 80.5 degrees. The next section is about ambiguous triangles, and you are going to try to draw both triangles that satisfy the description. So suppose you're given these dimensions, triangle ABC, where A equals 3 centimeters, C equals 5 centimeters, and A, the measure of angle A, is 30 degrees. And try to draw that triangle in two different ways, and then try to calculate the measure of angle C and the length of AC for each one. Here's some help on that ambiguous triangle. Again, I started drawing using the angle that they gave me, and then I drew side length C, and I know side length A is going to be opposite angle A, but look at the ways that I can draw it. I could either draw it back this way, 3 centimeters, or I could draw it out this way, 3 centimeters. And both can be true, but they both give a different length of AC, and they both give a different measurement for angle C, right? Here's an option for angle C, and here's an option for angle C. One is obtuse, one is acute. They are both satisfying the description of the triangle given. That's why it's called an ambiguous case, because the information given doesn't tell you exactly what triangle to use. If you get a problem like this, you'll actually have to solve for both cases. So here, I would need to solve the length. I would need to find the length of A and the second option of C right here, and also find the length of the other option for C, which is right there. I would need to find the angle for C2 and the angle for C1. Okay, on the rest of page 5, you have a lot of space for some notes. And what we're doing is relating the Pythagorean theorem. Relating the Pythagorean theorem to the trig identity. To the trig identity sine of theta squared plus the cosine of theta squared equals 1. A couple things to note here. This right here, sine squared of theta, this is actually read the sine of theta squared, but because this gets a bit cluttery when we're talking about trig and working with trig identities and ratios and proofs and all that kind of stuff, we are able to write it just like this. Okay, so it doesn't actually mean take the square of sine. Okay, that doesn't mean anything. That would be a meaningless statement. It's like, that would be like saying take the square of addition. That doesn't make any sense. Okay, so it's the sine of theta, and then you square the whole thing. What else is it not? It is not this. It's not take the square of theta and then sine it. Okay, that's what this would be. And that can happen. That's not what we're doing. Okay, it's taking the square of the sine of theta, and we write it like that. Okay, so this does kind of look like the Pythagorean theorem, right? You've got something squared and something else squared and 1. So basically what we're showing is that this is C squared, right? This is going to be the hypotenuse squared, and that's going to make sense inside the unit circle. If you recall from the trig unit in grade 11, you'll know that no matter what this angle is, it has a terminal arm, and the point where that arm meets the unit circle we often call P, and it has the coordinates cos of theta, sine of theta. That means that this angle right here, if it is theta, that just means any angle, that the distance that this point is from the y-axis, so along the x-axis, the distance that's traveled here is represented by the cosine of theta. It's equal to the cosine of theta. And similarly, the y-coordinate is the sine of theta. So the y-coordinate is the distance of this point from the x-axis. This is all by creating a right triangle inside the unit circle. So if we're dealing with a right triangle, we know we're inside the unit circle, which gives us a hypotenuse or a radius of 1, then what we have is just this distance in x and the distance in y equals our, you could use the equation of a circle and go r squared, or you can think of it as side length A, side length B, side length C, in which case you get a squared plus b squared equals c squared. And we can sub in what we know. Well, we know a is the value of the cosine of theta, and we're going to square that, and I'll rewrite it just this way first. And b is the sine of theta, and we're going to square that, and that's going to equal c squared, which is 1 squared, which is just 1. And I'm going to rewrite that simplified. We've got the cosine of theta squared plus, and I'm actually going to rewrite it with sine first because that's how it is in the identity. So we've got sine squared of theta plus the cos squared of theta equals 1. And there's our primary trig identity used in the unit circle, because we know that the distance along the x-axis is the cosine of theta, and the distance along the y-axis is the sine of theta, and we just apply the Pythagorean theorem, and you end up with this trig identity. Okay, we're going to talk about some special angles inside the unit circle. I'm going to explain how they work, and then we're going to just apply them. So you have a diagram that looks something like that. You have a radius drawn in it, and you have a right triangle completed in it. Okay, these angles are 45, which means this one is 45, and we can label the sides, we can label the angles. This is O for origin, this is P for the point where the ray crosses the unit circle or meets the unit circle, and then the last one I'm going to call point N. So we have triangle PON, where angle N is a right angle. Angle PON, so angle O and angle P are both 45 degrees. This is a right isosceles triangle. So an isosceles triangle because the two bottom angles are the same. What does that mean? That means that these two side lengths are also the same. Okay? So since triangle PON is a right isosceles triangle, PN equals ON. They are the same length. Then applying the Pythagorean theorem, we end up with, if we were going to use the Pythagorean theorem, we could say that Pn squared plus On squared equals OP squared, which is the hypotenuse. Because Pn is the same as On, we can write this as, we could change this to On squared, and then we'd have On squared plus On squared, which is 2On squared. And OP is the hypotenuse in a right triangle, in a unit circle, so we know that's going to have a length of 1, and 1 squared is 1. So this is what we can reduce it to, and our goal here is now to find the length of ON. Okay? Well, what would I do to find the length of ON? I could divide both sides by 2. Gives me ON squared equals 1/2. And then I can take the square root of both sides. Okay? So that will give me ON equals the square root of 1/2, or that can also be written as the square root of 1 is 1 over the square root of 2. So you might see it this way sometimes, and sometimes you might see it this way. They're both equal. They're the exact same thing, 1 over the square root of 2. So NP equals ON equals the square root of 2. So this length right here, from the origin to n along the x-axis, is 1 over the root of 2. And since ON equals PN, they both equal 1 over radical 2, then this vertical height, the distance along the y-axis here, is also 1 over radical 2, which tells us the coordinates of this point. Both coordinates are 1 over radical 2. Okay? Then, comma, the coordinates of P are 1 over rad 2, 1 over rad 2. This probably seems confusing and you don't know why I'm doing it, but you're going to be talking about point P at different spots around the unit circle so much. This is not going to be foreign for very long. Okay? If we can get, so we now actually know the cosine of 45 degrees is 1 over radical 2, and the sine of 45 degrees is 1 over radical 2, right? Because we said that point P is also represented as the cosine of theta, comma, the sine of theta. Okay, so now you know the cosine of 45 is always going to be 1 over radical 2. The sine of 45 is 1 over radical 2. And you can actually get the tangent of 1 over 45, the tangent of 45 degree angle as well. I'm going to write down the two things that we just did. Cosine, let's do the sine first, because that's, so the sine of 45 is 1 over radical 2. The cosine of 45 degrees is 1 over radical 2. And tangent of theta is always sine of theta over cosine of theta. So the tangent of 45 degrees is actually 1 over radical 2 over 1 over radical 2. Do you know how to reduce that? Something in the numerator, something in the denominator that are exactly the same. Just 1. And you can make connections between that and the length of your unit there as well. Okay, so how do we go around the circle then and get more of these angles? Okay, so I'm going to erase all this. And we're going to talk about the rest of these circles. We have a 45 here where the coordinates are 1 over radical 2, 1 over radical 2. Well, what about this one over here? What you'll notice is that it's the exact same vertical height, both positive. So the y-coordinate is pretty easy. And the x-coordinate, well, it's exactly the same distance from the y-axis to our original point, and we're going to go the same distance into the negative. So all that happens here for this point is that the x-coordinate is now negative 1 over radical 2, but the y-coordinate stays the same, 1 over radical 2. Well, what angle would this be? What did we actually just figure out? You now know the sine and the cosine of the angle 135 degrees. Right? 90 plus 45. Alright, let's go another 90 degrees.
Is this the same circle?
You have different diagrams. You could do it on the next circle. And we'll do this one in blue. So now we've gone 135 and we're going another 90. So we're way over here at 225 degrees. And what do we notice about our coordinates? Well, now the x coordinate and the y coordinate should be negative, right? But it's just as far to the left of the axis, so the x coordinate is the same as the one above it, negative 1 over radical 2, and the y coordinate is just flipped, negative 1 over radical 2. So now you know the cosine and the sine of 225 degrees. And you only needed to memorize the 145 degree one in order to get these other two. All right, last one. Same theory applies. So here, now it's 270 degrees plus 45, or you can think of it as 360 minus 45. Either way, in degrees, tight circle in there. Shouldn't start there though. What do we have an angle of? We have an angle of 315 degrees. And you know the coordinates of it. The x coordinate is going to be positive again, so that's 1 over radical 2. The y coordinate is now still going to be negative 1 over radical 2. Okay, these are special angles. 45 degree angle is a special angle because the coordinates are the same, and if you memorize the 45 degree angle, the cosine and the sine, you will also be able to do the cosine and sine of 135, of 225, and of 315. You'll also be able to do the tangent, because tangent is just the sine over the cosine every single time. Okay, for 30 degree angles, the proof is a little bit more challenging, but basically we're going to duplicate the right triangle that we have. So we're going to flip it upside down, and you're going to see how bad my drawing is. Your drawing should end up looking something like this. And that will enable you to draw a straight line all the way down to that new point. So again, we have O for origin, we have P, I'll do that one in black. Here you have N, where it meets the x-axis, that's point N. And then down here, where we've reflected it, we're going to call that P prime. Okay, that is a new point P, but it's based on the reflection here. So if we took the angle 30 and we flipped it over, we're essentially doubling that angle. What is the bigger angle here going to be then of this triangle? What's this whole angle going to be if it's the angle 30 twice? It's going to be 60. And because we've only reflected our triangle, OP prime is equal to OP. Okay, so it's an isosceles triangle where this is 1 and this is 1 because we're in the unit circle, and it has this interior angle here is 60 degrees. Well, in an isosceles triangle, P and P prime are going to be the same angle as well, and turns out that 180 minus 60 is 120, 120 divided by 2, all of these angles are going to be 60. So we've actually created an equilateral triangle inside the unit circle, which means that the length from P to P prime, this length right here, is also 1. Okay, all of that just to find out that if we know that the whole length from here to here is 1, P prime equals 1, therefore Pn equals 1/2, right? Because Pn is half the length from P to P prime. Good? Now we know the hypotenuse of OPN, and we know this side length. So we can use Pythagorean Theorem to find the length ON, okay? And I'm going to use Pythagorean Theorem like this. We've got ON squared is going to equal to OP squared minus NP, or PN squared. Okay, carrying on here, we don't know what ON is, but we know OP is 1 squared, which is 1, and we know PN is 1/2, which squared is 1/4, which means that ON squared is 3/4. Take the square root of both sides. You end up getting the radical 3 over radical 4, which can be reduced to radical 3/2. So the coordinates of point P here are, it's going on the x-axis, radical 3/2, and on the y-axis, 1/2. That's a 30-degree angle. So now you know the cosine of 30 degrees and the sine of 30 degrees. And if you wanted the tangent of 30 degrees, you would just put sine over the cosine and do some clever math, okay? Now, how does that help us get all those other awkward ones? Well, you guys have another point on your triangle. So here would be like a 45 degree, which we already did. Here is the 60 degree. Well, what you'll notice about a 60 degree triangle is that you actually end up forming another triangle, right triangle, with the y-axis, and it ends up being the exact same triangle, except the x distance of radical 3/2 is now the y distance, and the y distance of 1/2 is now the x distance from the y-axis. Okay? So without going into too many details there, just talking about that 60-degree angle, and I'll do it in red so that it's the same as my drawing. Therefore, sine of 60 degrees equals, and this is the vertical, right? Radical 3/2. The cosine of 60 degrees is 1/2, and the tan of 60 degrees is going to be the sine over the cosine. So that's going to be radical 3/2 over 1/2, which reduces, these guys are both over 2, so you can actually just multiply top and bottom by 2, which will give you radical 3/1, which is just radical 3. So the tangent of 60 is radical. So when working in a unit circle with an angle of 30 degrees, we found out that the point where the terminal arm meets the outside of the unit circle, the coordinates of that point are radical 3/2 and 1/2. And then we discovered that for a 60-degree triangle, really all we're doing is reflecting this triangle over the line y equals x, which is just going to make x and y swap positions. So here, the sine of 60 degree is equal to the cosine of 30 degrees, which is radical 3/2, and the cosine of 60 degrees is equal to the sine of 30 degrees, which is 1/2. And now as our tangent of theta, or our tangent of 60, here I should write 30, okay, it's simply going to be the inverse of the tan of 30, because instead of being sine 30 over cos 30, it's sine 60 over cos 60, which was just a flip of the numerator and the denominator. We're going to end up with 1 over radical 3. And this is going to allow us to know the coordinates of, to know the x and y for every single multiple of 30. So once we get beyond the 90 degree, as we get to 90 degree, sine becomes 1 and cosine becomes 0. We talk about that in a second. But as we move over to 120, we see that the only difference between this coordinate here and 120 has the exact same y coordinate, but the x coordinate is now negative 1/2. instead of positive 1/2. So as we go down this list, we can take the sine of 120 degrees, and it's going to have the same numerical values as the sine and cosine of 60 degrees, but the x-coordinate here, the cosine, is going to be negative 1/2 instead. Here we go. The sine of 120 is the exact same as the sine of 60. That's radical 3 over over 2. The cosine of 120 degrees is going to be negative 1/2. And what's that going to do to the tan of 120 degrees? Well, it's going to be the same as the tan of 60, just negative. Negative 1 radical 3. Okay? Well, let's go ahead down here and we'll pass the 45-degree angle. We'll go down here to 180 minus 30, okay, which is 150 degrees. And my diagram's not great, but you should see that it is the same height. So the y-coordinate will be the same as our original here. The x-coordinate will be the same, but negative, okay? So we've got the sine, drop it down a little bit, the sine of 150 degrees, which is the y value. It's going to be negative, it's still going to be 1/2. And the cosine of 150 degrees is going to have the same numerical value as here, the x-coordinate, but it's going to be negative, so we're looking at negative radical 3 over 2. And I'm just going to look up in my chart where I see those numbers already, 1/2 and radical 3 over 2. And here the tangent of 30 is positive radical 3, so I know that the tangent of 150, because it's going to end up having one negative factor if I do sine over cosine, is going to be negative radical 3. And you could keep going around the whole circle, and you should get the coordinates of every point around that circle. So again, you can represent these. The coordinates here are going to be the same as the coordinates here, the numerical, but they're both going to be negative, right? Instead of being positive this far along the x-axis, I'm going to be negative that distance. Instead of being positive y up to here, we're going to be negative y down to there. So the sine of 210 is negative 1/2. The cosine of 210 is negative radical 3 over 2. And then look at what happens to the tan of 210. It now has two negative factors. So the tan of 210 is actually equal to the tan of 30. It's going to help us think about some of our properties later on. Another way to write this all the way around your circle is by actually writing the coordinates beside these points. So we've got cosine of theta, sine of theta. So here we got cosine of 210, which is negative radical 3 over 2, and the sine of 210, which is negative 1/2. And there's my point, I'll put it back there. And you go all the way around the circle doing those values. You're going to need this guy at 270 minus 30, which is 240, and this guy at 300, and this guy at 330, till you get all the way back to 0 or 360. Go ahead and try those on your own. A couple other keys when we're working in the unit circle. We've been talking about the coordinates being the cosine of theta and sine of theta, where cosine represents the distance from the y-axis, or represents the distance along the x-axis, and sine represents the distance along the y-axis. So what is happening as our angle gets closer and closer and closer to 90 degrees? What's happening to our x value? Well, it starts out being 1, and then, here at the the cosine of 30, we said it was radical 3 over 2, and then over here it's only 1/2, and it's actually getting closer and closer and closer to 0. It's getting closer and closer to not having any x value. The x-coordinate up here is 0, right? So this would be 0, 1, which tells us two things. It tells us that as we move toward an angle of 90 degrees, the cosine of theta approaches 0, and the sine of theta approaches 1. Go ahead and fill in those blanks on your worksheet. And homework is also listed on the bottom of your worksheet. Questions from several different sections, just to make sure you know what you're doing, you're ready to dive into grade 12 trig.